Hello and welcome back. Turning my heat up. Welcome back to the May 2025 IB Chemistry Paper 2 exam walkthrough. Fun fact, I've done the calculation. These videos are now 5 hours long and counting. So let's continue. If you haven't already, the SL version of this question 1 is in this video here. I'm not going over the SL subparts that are in common with HL. I'm just going over the HL additional marks. In this video, it'll be for 1C and 1D. Okay, so this part is essentially centered around this cyanide ion that forms complex ions. Very common HL type question. The big thing with part 1 is to state the precise type of bond formation between the cyanide ion and the iron ion. And whenever we're doing this, we kind of want to draw out, like, you don't have to draw out the structure, but I like to just visualize things because I suck at visualizing things. And so you have your nice iron atom, and then you have a bunch of cyanide, Eschen minus Eschen minus Eschen minus, oh, that's gross. I need to reverse that. Cn minus 1, 2, 3, 6. Okay, so you've got this kind of guy. Oh no, come back. There you go. This kind of guy happening. And I'm putting Fe plus for now because we haven't calculated the charge that is on iron. We know it's going to be a cation. We just don't know exactly what it is. Okay. And so complex ions you want to maybe think, oh, this is just a basic kind of covalent bond. However, you should recognize, or even an ionic bond, whatever. However, you should kind of recognize that you kind of have these minuses and these pluses. Okay. Oh, this should be reversed. This minus should be. The minus is on carbon. Okay. And so we don't tend to draw out this full structure, but all of these carbons this is rare for carbon, by the way. Almost never happens, but carbon does, in fact, in the cyanide anions have a lone pair of electrons. Okay. And so with that, you kind of should kind of start to be like, oh, this kind of looks like the hydroxide ion, right? Like it's kind of similar. To where it's a lone pair of electrons, it's a minus, and hydroxide ions are very much so well known as our big nucleophile in organic chemistry. And so there's a big intersection between complex ions, organic chemistry, and acids and bases, which involves complex ions, electrophiles, and nucleophiles, and Lewis acids and bases. Okay. And so Lewis acids I always remember this because Bronsted-Lowry acids donate a proton. And so it is opposite day for the Lewis acids, and so they accept a lone pair of electrons. Okay, so much for like Lewis acids. They accept a lone pair of electrons. Meanwhile, a Lewis base donates electrons. And so these cyanide anions are essentially acting as Lewis bases here because they are able to donate that lone pair of electrons. Okay, and so these bonds that are forming is all of the electrons that are in that bond are coming from the ligands. Okay, as these cyanide anions are these ligands that are acting as Lewis bases, donating electrons, and this iron is accepting them. And so this specific kind of bond is known as a coordination bond. Coordination. I'm going to put coordinate bond. I believe there's another word for it that was in the old syllabus. I forgot what it's called. Let me look it up real quick. You also could say dative bond, coordination, covalent. All of those are options. Okay. And so that is what that type of bond is. And that's kind of ideally the thought process you should go whenever you're thinking about it. For the oxidation state of iron, the way that you need to do this is similar to oxidation state of everything else. Is you have your iron, and then all of your cyanide ions are Cn minus. Okay, and you have 6 of them. So you have +6 -1. Okay, so you have 6 of these ligands having -1 charge each. And overall, this whole complex has a charge of 4 minus. Okay, and so then you're just going to do some math. So it's just going to be Fe -6 is equal to -4. And then -4 + 6 is going to be +2. Okay. Also, I'm going to be honest. If you're ever doing a calculation like of oxidation state of a transition metal, there's like a 50% chance it's going to be +2. So if you guess +2, like if you have no idea, just guess +2. I'm not going to lie. It's probably a good piece of advice. Anyways, this part 3. This part 3 is a very, literally it's on every exam, and every exam season there's a thing in the subject notes where they rant about the fact that students still get this wrong because it's in every exam season. It's very predictable. And so it's explained why transition element ions such as FeSN6 4- are usually colored. Okay. And so with this, one of the first things that we want to do is essentially explain, because it's about transition element ions. Okay. Essentially define what the heck that transition element kind of is, like what kind of makes it a transition element ion in the first place. And so I'm just going to put TM. So TM ions, they have these partially filled d orbitals. Okay, that is exactly what defines a transition element. Okay, partially filled d orbitals, as that is the requirement in order to be defined as a transition metal. Okay, whenever you have these ligands, like these cyanide ions, is they approach, and so you have this geometry of the d orbitals is they essentially, we don't learn too much about it, but you have the different axes of the kind of x, y, whatever. I'll put an image here because I'm really bad at explaining this without this visual. Is that they essentially, you have this kind of different d orbitals in these different geometries, and so based on the approach of the ligand, is some of those orbitals are closer to the ligand, some of them are more further away, and so they split into higher and lower energies. Okay. And so that is usually that second type of mark, is that they ligands cause them to split. I'm gonna put d orbs to split to high and low energy. Okay. Once again, we are abbreviating here because I talk way faster than I can write. Okay. And so it's causing them to split into higher and lower energy. And so whenever that happens, is essentially it can absorb a wavelength that corresponds to that energy gap and allow an electron to essentially be promoted from the lower to the higher level. So the way that we can kind of say this is essentially that energy gap absorbs wavelength to promote the electron from low to high energy level. Okay. And so now this is where it gets different. Is normally on the older mark schemes is they would accept that for this kind of final mark as one of the options is they would accept that the complementary color of the wavelength absorbed is emitted. Actually, I'm going to interject. This is me from the future here, editing the video, is that actually, okay, I double checked actually some of the old questions, is that whenever they're asked specifically about why a complex is a specific color, they do accept the complementary color is seen. However, whenever they're asking about whenever complexes are generally colored, they have never accepted the complementary color thing. I just never failed to notice that until this exam. Okay, thank you, me from the past. Continue. And it specifically says do not accept that, and that you must instead, they would only accept is that if you reference the fact that this energy gap essentially corresponds to the visible region of wavelength, corresponds to visible wavelength. Okay, can my camera focus? There you go. Because it seems that whenever it's explaining why they are colored, it's that they want more of a focus on why they are colored in the first place and not so much of what color is being shown, if that makes sense. And so that is a new thing to note with these new 2025 mark schemes. And now we're going to assume that this will probably be a pattern going forward, because they probably will still ask this question every few exam seasons because it's a common one, right? And so that is how that question is. It's still approached pretty much exactly the same as it was previously, but then that final mark of complementary color no longer is accepted, and it has to be something along the lines of answering about the visible region instead. Okay, and so for this part 4 it's literally just a basic kind of equilibrium constant type of calculation. And so it gives us this concentration of Fe2 plus. And so our overall solution of the complex ion is 1 mole decimeter negative third. And to determine the value of the equilibrium constant for the formation. And so in order to do this, is we kind of want to write out the equation for the formation of the ion. Okay, is that we have our Fe, come back, 2 plus our cyanide ions forming our FeCN, where is it? Where it is a 6 to then the 4 minus. And so we need to balance our equation. And so we need to balance our cyanide. So it'll be 6. Now we can write the equation for the equilibrium constant. So our K is going to be equal to the FeCN 6 4 minus over the concentration of Fe2 plus times the concentration of cyanide times 6. Okay, and so we have the concentration of our overall complex. We have the concentration of Fe2 plus, but we do need to solve for the concentration of cyanide, and we can just use basic stoichiometry for that from our equation. Okay, and so it is just going to be that we have, what's it called? For Fe2 plus is we have or concentration. And so since they're in a ratio of 1 to 6, is you're just going to multiply by 6. Okay, so a concentration of Cn minus is just going to be equal to that 1.32 times 10. Not 1.32, sorry, my bad. Listen, I'm having a stroke. Okay, it is our 2.2 times 10 to negative 7 times 6. Okay, and so if we do that, then we end up getting that 1.32 times 10 to the negative 6. Okay, and so now we can just plug it in to our overall equilibrium constant expression. So we have our ion concentration, 1 divided by our Fe. So that would be our 2.2 times 10 to the negative 7 times the concentration of our cyanide ion, 1.32 times 10 to the negative 6, except we have to raise that to an exponent of the 6. Okay, and so if we put that all into our calculator, we end up getting the equilibrium constant as 8.59 times 10 to the 41st. Okay, so very simple calculation. I'm not gonna lie, I was kind of panicking here because I kind of forgot stoichiometry existed. Because I was like, how do I find cyanide? It's like, is there an assumption I'm missing? No, it's just stoichiometry. That's it. So yeah. For this part 5, the final subpart of this video is the outline giving a reason whether the complex is going to be a stronger or weaker oxidizing agent than Fe3 plus. And so we are given the electrochemical kind of reduction data for the complex ion as being plus 0.37. So that is its reduction potential. So we need to find the reduction potential of Fe3 plus. So we're going to go over to our data booklet. There we go. And so it is important to note that our for our reduction potential of the what's it called complex is that our complex is going to be on the left side of the equation. It's going to be a reactant, okay, because it's the reduction potential, right? Because there will be options in our data booklet where Fe3 plus is on the kind of either side, I'm pretty sure. So we're going to find Fe3 plus over here. There we go. So that would be this one as 0.77. And so whenever we're looking at our kind of series is you have to remember that up here is going to be more likely to be oxidized. The more negative the value is, the more likely to be reduced, the more positive the value is. Okay, and so since we are comparing it to 0.37, so I'm going to put over here of Fe 3 plus E cell is equal to 0. Is it 77? Yeah, 7777 volts. Okay. And so it's asking about whether it's a stronger or weaker oxidizing agent. Okay. And so the stronger the oxidizing agent, so I'm going to put strong ox agent, is going to be more likely to be reduced. Okay. Reduced. Okay. And so the more likely to be reduced, the more positive the value is going to be. Okay. And so since it has a less positive value than the for Fe3 plus, so I'm gonna put our complex ion, less positive value, which essentially just means that it is going to be less likely to be reduced, and then therefore a weaker oxidizing agent. Okay, so it's just based on the E cell values. Okay, it is also important to note that this question is asking about specifically whether Fe, the ion, is a stronger or weaker oxidizing agent. If you just said Fe3 plus is a stronger or weaker, like in this case, I took this myself and I kind of didn't read it as careful as I should, and I kind of put in my box of, oh, Fe3 plus is going to be the stronger oxidizing agent. Seeing it more as kind of like a compare, which technically still wasn't, I'm not sure if they would take that as answering the question. I always like to emphasize the fact that I've never been an examiner. I have no idea how strict or how lenient they are on the marking schemes. And I don't even think they put that as an alternative answer, which would kind of insinuate that would be an option. So just to be careful there and always to make sure you're kind of answering the question that is at hand. So that is that question 1C though.